Have you ever stopped to wonder about the simple chemistry that's happening all around you? I mean, in your kitchen when you're making ice cream, or on the roads in the middle of winter, or even inside your car's engine? Well, we're about to dive into the hidden science behind all these everyday things. And believe it or not, it all comes down to something called colligative properties.
So let's start with something fun and honestly pretty delicious, making homemade ice cream. If you've ever seen an old school recipe, it probably calls for a big bucket of ice and a whole lot of rock salt.
But wait a minute, here's our first puzzle. Why on earth are we adding salt to ice to make something else freeze? It feels totally backwards, right? You add stuff to ice and the entire mixture actually gets colder than regular ice. How in the world does that work? And then there's the flip side of that puzzle. Come winter, we see those big trucks out there spreading salt all over icy roads. But in this case, the goal is to make the ice melt. So hold on, salt can make an ice mixture colder, but it also makes road ice just disappear. What is going on here? Okay, so there we have it, our two everyday chemistry puzzles. They really seem like complete opposites, don't they? But they're actually two sides of the very same scientific coin. The thing that connects making ice cream and de-icing roads, well, it's not magic, even though it kind of feels like it. It's actually a simple and incredibly powerful rule in chemistry. And once you get it, a lot of things about the world are just going to click into place. So let's get right to the heart of it. We're going to call this the numbers game rule. Now, the official name is a little more scientific, but the idea behind it is surprisingly simple. And here it is. The fancy scientific term is a colligative property. But the most important part is right there on the screen. It's a property that depends only on the number of particles you dissolve in a liquid, not what those particles actually are. Here's a great way to think about it. In the world of colligative properties, the liquid doesn't care if you're a particle of salt or a particle of sugar. All it cares about is how many of you there are. It is all about quantity over quality. Now, this is where it gets really interesting. This is how some compounds kind of cheat at the numbers game. See, when you dissolve something like glucose, that's sugar, one molecule just stays as one particle floating around. But when you dissolve sodium chloride, which is just regular table salt, each little unit splits into two particles, a sodium ion and a chloride ion. And then you have something like calcium chloride. That one splits into three. It instantly triples its power. And this chart just lays it all out visually. Because salt splits into two particles, it has double the effect of sugar. And calcium chloride, splitting into three, is even more powerful. This right here, this is the secret weapon behind everything we're talking about today. So, what does winning this numbers game actually get you? What does it do? Well, it creates three really distinct and powerful effects on whatever liquid it's dissolved in. Let's break them down one by one. Okay, the first big effect is something called vapor pressure lowering. I know, that might sound a bit technical and boring, but the idea is actually super easy to picture. Think about it like this. In a glass of pure water, the molecules at the surface can just easily escape and turn into vapor, evaporate. But when you add solute particles, like our salt, they get in the way. They're like tiny little roadblocks right at the surface, making it much harder for the water molecules to make a run for it. This lowers the vapor pressure. All right, on to the second effect. And this one is the key to our puzzles. It's called freezing point depression. The name pretty much says it all. It makes the freezing point go down or get depressed. For water to freeze, all its little molecules need to line up in this very neat, orderly crystal structure. But just like they did at the surface, our solute particles get in the way. They're like little troublemakers, disrupting the whole process and making it way harder for those ice crystals to form. So, to overcome all that disruption, the temperature has to get even colder. And our third and final effect is pretty much the exact opposite of what we just talked about. It's called boiling point elevation. And you guessed it, this time the boiling temperature goes up. Now, this connects right back to that first effect we mentioned. Remember how those solute particles made it harder for water to escape as vapor? Well, boiling is just water escaping really, really fast. And since the vapor pressure is already lower, you have to pump in more energy, more heat, to get those water molecules to finally break free. That means the whole solution boils at a higher temperature than pure water would. Okay, so we've got our three effects down. Lower vapor pressure, a lower freezing point, and a higher boiling point. Now, let's take that knowledge and finally solve those puzzles we started with. All right, let's go back to that ice cream maker. Why are we dumping all that salt on the ice?
It is all about freezing point depression. The salt dissolves on the wet surface of the ice and it creates this super cold saltwater slush that wants to be a liquid even at temperatures way below freezing. But for the solid ice to melt and join the slush, it needs energy. It needs heat. And where does it get that heat? It rips it right out of the ice cream container, making your dessert freeze solid. It's brilliant.
And check this out. Here's another awesome example that uses two of our effects at the same time. The antifreeze in your car. In the winter, it lowers the freezing point of the water in your engine so it doesn't turn to a block of ice and crack everything. And then in the summer, it uses boiling point elevation to keep that same water from boiling over and overheating the engine. How cool is that? It's like a year-round chemical superhero. So, we've seen the science and how it works. For our last section, let's just take a quick look at why all this matters in the real world. We know from that chart earlier that some compounds, like calcium chloride, are technically more powerful because they release 3 particles instead of just 2. So, why do we almost always use regular table salt, sodium chloride, for stuff like de-icing roads? Well, the answer is pretty simple. It's where science and practicality have to meet. Sodium chloride just hits that perfect sweet spot. It's cheap, you can get it anywhere, and it's safe to handle. Plus, because it splits into 2 particles, it's still twice as effective as something like sugar would be. It's the perfect balance of chemical power and real-world economics. See? It's not just about science, it's about smart science.